Okay, chapter 21, alternating current circuits and electromagnetic waves. We're going to refer to alternating current circuits as AC circuits, and we're going to refer to electromagnetic waves as E&M waves. So let's get started with the PowerPoint. Oops, jumped the gun a little bit. We rely on the power provided by alternating currents to use our TVs, computers, and electric appliances, among other things. In this topic, we'll begin our study of AC circuits by examining the characteristics of a circuit containing a source of EMF and one other circuit element, a resistor, a capacitor, or an inductor. Then we will see what happens when these elements are connected in combination with each other. We will also look at electromagnetic waves, which are composed of fluctuating electric and magnetic fields. Electromagnetic waves, E&M waves, in the form of visible light, enable us to view the world around us. Infrared waves warm our environment. Radio frequency waves carry our television and radio programs, as well as information about processes in the core of our galaxy. And X-rays allow us to perceive structures hidden inside our bodies and study properties of distant collapsed stars. Light is key to our understanding of the universe. Okay, here we have a series, the figure is a series circuit consisting of a resistor R connected to an AC generator, designated by the symbol shown in the figure, a little tilde. It looks like a little tilde. It's like a little sinusoid. It's a sinusoid generator. An AC circuit consists of combinations of circuit elements in an AC generator or an AC source, which provides the alternating current. The output of an AC generator is sinusoidal and varies with time according to the equation here. Delta V equals delta V max sine 2 pi f t. Of course, 2 pi f is omega. And the f in most cases, in most household circuits, is 60 hertz. Delta V is the instantaneous voltage, delta V max is the maximum voltage of the AC generator, and F is the frequency at which the voltage changes, measured in hertz. And as I said earlier, in US households, it's 60 hertz. In European households, it's 50 hertz. Let's consider a simple circuit consisting of a resistor and an AC source as shown in the figure. Take a look at the current versus time and voltage versus time curves for the circuit in the previous slide. At point A in the curve, the current has a maximum value in one direction, which we will arbitrarily call the positive direction. Between points A and B, the current is decreasing in magnitude, but is still in the positive direction. At point B, the current is momentarily zero. It then begins to increase in the opposite negative direction between points B and C. At point C, the current has reached its maximum value in the negative direction. Notice that the current and voltage are in step with each other. Because the current and the voltage reach their maximum values at the same time, they are said to be in phase. As you can see, also you can see that the average value of the current over one cycle is zero, because the current is maintained in one direction, the positive direction, for the same amount of time, and it's in the same magnitude as it is in the opposite direction, the negative direction. The direction of the current doesn't matter in terms of the resistor. The collisions between electrons and the fixed atoms of the resistor result in an increase in the resistor's temperature no matter which direction the current flows. Okay, here we have a plot. The current in the resistor is a function of time. And then we also have underneath that, we have the plot of the square of the current in the resistor as a function of time. Okay, let's quantify the discussion. Remember that the rate at which electrical energy is dissipated in a resistor is the power shown here. Power equals I squared R, where I is the instantaneous current in the resistor. The little I is used for the AC circuit, as opposed to a capital I for a direct current. The heating effect of a current is proportional to the square of the current, so it makes no difference whether the sign associated with the current is positive or negative. Note, though, that the heating effect produced by an alternating current with a maximum value of Imax is not the same as that produced by a direct current of the same value. The reason is that the alternating current has this maximum value for only an instant of time during a cycle. The important quantity in an AC circuit is a special kind of average value of current called the Rms current, which is the direct current that dissipates the same amount of energy in a resistor as the actual alternating current. Rms stands for root mean square. The top graph shows the alternating current. If we found the average of this current, it wouldn't be very useful because the average is 0. On the other hand, the Rms current is always positive. To find the Rms current, we first square the current, then find its average value, and finally take the square root of this average value. That means the Rms current is the square root of the average of the square of the current. Because I squared varies sinusoidally, the I squared equals sine squared 2 pi ft. Because it varies sinusoidally, the average value of I squared is 1/2 Imax squared, as shown in the bottom in the bottom graph. The relationship between I-Rms and Imax is given here. I-Rms is equal to Imax divided by the square root of 2, or 0.707 Imax. That 0.707 is going to come up a lot. This equation says that an alternating current with a maximum value of 3 amps produces the same heating effect in a resistor as a direct current of 3 over the square root of 2 amps. We can now say that the average power dissipated in the resistor that carries alternating current I is shown here. Power equals I squared Rms times R. We can talk about alternating voltages in the same way in terms of Rms voltages with the relationship here. Vrms is equal to Vmax divided by the square root of 2, which equals 0.707 times delta Vmax. Delta Vrms is the Rms voltage, and delta Vmax is the maximum value of the alternating voltage. When people talk about measuring an AC voltage of 120 volts from an electric outlet, they actually mean an Rms voltage of 120 volts. A quick calculation using this last equation shows that such an AC voltage actually has a peak value of about 170 volts. Okay. In this topic, we use Rms values when discussing alternating currents and voltages. One reason is that AC meters and voltmeters are designed to read Rms values. Also, if we use Rms values, many of the equations for alternating current will have the same form as those used in the study of direct current circuits. The table here summarizes the notations used in this topic. We have the instantaneous value, that's the small I and the small v. Maximum values are capital Vmax, Imax. Rms values are capital V and capital I, but with the Rms subscript underneath them. The Rms, again, meaning root mean square. Now let's consider the series circuit shown in the figure, which consists of a resistor connected to an AC generator. A resistor impedes the current in an AC circuit, just like it does in a DC circuit. That means Ohm's law is valid for an AC circuit, and we have the relationship shown. The Rms voltage across the resistor is equal to the Rms current in the circuit times the resistance. This equation is also true if maximum values of current and voltage are used. So we can use the Vrms equals I-Rms times R, or delta Vmax equals Imax times R. Okay, this ends the resistors in an AC circuit section. The next section we will discuss is section 21.2, capacitors and inductors in an AC circuit. We're going to do 21.2 and 21.3 together.